Welcome to all of you. Now we discuss about directional derivatives, multivariate calculus 1 or semester 3, paper CC-7 Mathematics Honors, University of Calcutta. What is the directional derivatives? Let f be a function of two independent variables x and y be defined over a domain D, a subset of Cartesian plane R2. Let P be any point with coordinates a, b, be any point on D. Let N be a neighborhood of the point P such that N is a subset of D. Let Q with coordinates a plus h, b plus k belongs to N. If alpha be the angle that the line joining the PQ makes with positive direction of x-axis, then the direction cosines of PQ are L equal to cos alpha and M equal to sin alpha. And if rho equal to root over of h square plus k square, then h equal to rho cos alpha and k equal to rho sin alpha. And rho tends to 0 as q tends to p. Then the directional derivative of the function f xy at the point AB in the direction alpha along the semi-axis semi-line PQ is given by d alpha f at the point AB equal to limit rho tends to 0 f of a plus rho cos alpha comma b plus rho sin alpha minus f ab whole divided by rho if this limit exists. This is the point P, this is the point Q, and this is the H, and this K, and this PQ distance is rho, and this angle is alpha. Now, if alpha equal to 0, then this limit H tends to 0, then K equal to 0. So, A plus H comma B minus AB whole divided by H, limit H tends to 0, and this called with del F del X at the point AB. If alpha equal to pi by 2, then this directional derivative is the partial derivative with respect to y at the point AB, limit k tends to 0, f a comma b plus k minus f a comma b whole divided by k if these limits exist. Now, very important theorem, if phi be a function of x, y, z, be a scalar point function. Here x, y, and z are independent variables and possessing continuous first order partial derivatives, then the directional derivative of phi at the point P x, y, z along a line having unit vector e cap, this equals to L I cap plus M j cap plus N k cap is given by directional derivative in the direction e cap of the function phi at the point P, this equals to d phi ds at the point P, this equal to grad phi at the point P dot e cap. That is del phi del x L plus del phi del y M plus del phi del z N, where grad phi equal to del phi del x I cap plus del phi del y j cap plus del phi del z k cap. Here I cap, j cap, k cap are the unit vectors along the axis x, y, z respectively, the gradient of the function phi. Now the geometrical interpretation of the directional derivative. Let z is this is a dependent variable, this function f x y, here x and y are independent variables, be the equation of a surface defined in a domain D is a subset of Cartesian plane R2. So this picture, this is the figure, this is the surface, is the fxy, and this is the xy plane, and this is the domain of this function of the surface fxy, and let z0 equal to fx0 y0. This is the height x0 p point, this point is p point, x0 y0 z0. So this point a point, the projection of the point p on the xy plane, this point a with coordinates x0 y0 0, and so this height is the z0, and this a point is parallel to the unit vector u cap. This parallel vector, this is the u cap unit vector. So this we consider vertical plane. This is the vertical plane parallel to the unit vector u cap intersects the surface z equal to fxy in a curve C. So this plane parallel to the unit vector u cap, this plane cuts the surface in this curve C. This is the curve C. Then the directional derivative of fxy in the direction of u cap geometrically represents the slope of the tangent to the curve C at the point P x0, y0, z0. So this is the directional derivative at the point P in the direction u cap. Now the directional derivative and gradient vector. This the directional derivative of a function f xy at point p0 x0 y0 z0 belongs to D. The domain of the function f is a subset of R2 along the direction of the unit vector u cap. This is equal to Li cap plus Mj cap is given by d u cap f at the point p0. This is equal to grad f at the point p0 dot u cap, and or df ds at the point p0 equal to this modulus of gradient of f at the point p0 into modulus of u cap into cos theta. Theta is the angle between the gradient of f vector at the point p0 and u cap. So this is the unit vector u cap. So mod of u cap is equal to 1. So we get the modulus of grad f at the point p0 into cos theta. Thus, here the some important results. The directional derivative of a function f along u cap is the projection of the gradient vector of f on u cap. So this is the line along the u cap, and this is the gradient of f at the point p0. So the projection of grad f along the line u cap. So this distance, this p and this point. So this is the df ds at the point p0. This is the directional derivative, is the projection of grad f on the line in the direction of u cap. Remark 2, if theta equal to 0, then df ds, that is the directional derivative at the point p0, then the grad of p0, modulus of grad of p0. So cos 0 equal to 1. So this is the gradient directional derivative of f is considered along the direction of grad f. Then we get the maximum value of the directional derivative of f, which is equal to the modulus of grad f at that point. And remark 3, if theta equal to pi, then cos theta equal to this minus 1. So df ds at the point p0 is the directional derivative of the function f at the point p0 equal to minus of modulus of grad f at the point p0. So when the directional derivative is determined along the opposite direction of grad f, we get the minimum value of the directional derivative of f, and which is equal to minus mod of grad f at this point p0. Remark 4, if theta equal to pi by 2, then directional derivative df ds at the point p0 equal to grad f at the point p0 dot u cap. This equal to 0 because cos pi by 2 equal to 0. So directional derivative of the function f at the point p0 along the direction u cap, which is perpendicular to the gradient vector of f, is equal to 0. Remark 5, the maximum and minimum value of the directional derivatives are modulus of grad f and minus modulus of grad f respectively, and it acts along the unit vector grad f by mod of grad f is the unit vector along the grad f vector, and minus in the opposite sense the grad f by mod of grad f is the opposite of the directional grad vector, grad of f vector. And remark 6, the directional derivative of f at a point p0 is maximum or f increases most rapidly if it acts parallel to the vector grad f by mod of grad f. Remark 7, the directional derivative of f at a point p0 is minimum or f decreases most rapidly if it acts parallel to the vector minus grad f by modulus of mod grad f at that point p0. The directional derivative, this is the diagram of this directional derivative of the function phi at the point P. So d phi ds at the point P is equal to grad phi at the point P dot u cap. That is the mod of PQ vector. This is the line u along the unit vector, this line, and this is the grad phi at the point P. So this length, this PQ, is the projection of grad phi along the line u cap. This is the gradient, this is the directional derivative of phi at the point P along the line U cap. So here this is the XYZ plane. This is the surface Z equal to phi XY, and this point on the surface P. So this is the unit vector u cap cos theta I cap plus sin theta j cap. So this is the vertical plane along parallel to the vector u cap. So this plane cuts the surface this curve C at the point P. So this tangent is the this tangent direction. This is the gradient directional derivative uh, of this point. And so this is the projection P point, and this is the x-axis. This is the x-axis, direction of x-axis. So theta is the angle between this anticlockwise direction. This theta is the angle between the x-axis and the u cap. So this is the grad phi is the del phi del x I cap plus del phi del y j cap, and this del phi del x along the at the point P, that is the parallel to when y is constant. So this is the y equal to constant. This plane in this plane y equal to constant parallel to the xz plane cuts the surface this curve C at the point P. So this is the tangent at the curve this C at the point P. So del phi del x is the slope of at the point P y is constant. Now we use the directional derivative. This is the surface. This a of xy x square plus y square by 2. Suppose this plus 1. So this is the surface. This is the surface, and this is the point P. This is the point P. This point P, and at this point projection of this point in the xy plane. This is the x equal to 1 and y equal to 1. This is equal to 1, y equal to 1, and this is the point, and vector u. This vector u is the angle is 14 degree. If you change this angle unit vector in the direction u vector. So this is the direction of u vector. This red line is x-axis, and this y line is the y-axis, and this vertical line is z-axis. So this is the surface, and this is the unit vector. This with angle the x-axis is 32 degree, or say this the 65 degree. Then this vertical plane, this along parallel to this unit vector cuts this surface this, and this is the curve this surface this curve. So if we change this, so we get this curve uh, by cutting by this plane and this surface fxy, and this fxy equal to this. So this point is the projection is 1 1. This point at the point u with angle 86 degree. Then directional derivative we get this fu 1 1 is the 1.4. If angle equal to 0, then this directional derivative is this represents this u cap is along the x-axis, that is here y equal to constant. So y equal to constant. So this tangent to this curve this represents this del phi del x. If angle is 90 degree, then you get this plane. This plane is the parallel to the y-axis. This x is constant. So this tangent represents this on this curve at this point. Which projection is P on the xy plane with coordinates 1 1 in the xy plane. So gradient of this tangent represents the del phi del y. Here x is constant. This is the vertical plane parallel parallel to the yz plane. This y equal to constant. So this gradient is this of this tangent line represents the del phi del y at this point. If the angle is 180 degree, then we get this unit vector is this direction the opposite to the x-axis, negative x-axis direction, and this is the point is this point on this point. If you change this point you can change this point projection 1.6 and this point, so you get this. And if you can change the 180-degree, or this is the this red line is the direction of the unit vector, and this the vertical plane that cuts this surface this along this curve. And so at this point, this we get the directional derivative of this. So beautiful picture from GeoGebra, and you can clearly get the idea from this picture. Next, here vector differential operator, this grad, so I cap del del x plus j cap del del y plus k cap del del k, and this grad del vector is pronounced as del or nabla vector, and this operator del del x del del y del del z are the components of grad, which has the dual character, that is the an operator as well as vector. And the gradient in Cartesian coordinate system, and E3, the gradient of the scalar point of function fxyz is denoted by grad f or grad f function, and is defined by the vector point function grad f equal to I del f del x plus this grad f equal to this, where the partial derivative of a are assumed to be continuous. But the magnitude of grad f is this root over of x square plus fy square plus fz square, and the direction cosines of the gradient of a, this fx by mode of grad f, fy by mode of grad f, fz by mode of grad f. The geometrical interpretation of this gradient vector, this is the surface fxyz equal to c, and pxyz and q is the point, another point. So this is the point p, and this point q, this point q, at this point x plus del x plus y plus del y, z plus del z are two neighboring points in the surface. Then op equal to r vector, and oq equal to r plus delta vector, and pq equal to delta vector. So this is the vector pq delta vector. So limit q tends to p, pq vector equal to limit q tends to p delta vector, that is dr vector, which lies on the tangent plane P, and hence the direction of dr is along the tangent to the surface at P. So grad f dot dr equal to this. And thus grad f dot dr equal to 0 shows that the gradient of f is orthogonal to dr vector. So normal to the surface 1. So normal to the surface 1. And dr vector is the direction is this, dr vector is direction this, so gradient is the normal to this vector plane, normal to the tangent plane of this. And so this is the theorem, and we describe this theorem. And the note, this class note, you can get this class note pdf form in the description box. These some theorems on gradient 1 2 3 4 5 6 7, proof of 5, theorem proof of 5, proof of theorem 6, and proof of theorem 7. Here the tangent plane and normal line at a point on level surface. This phi xy is the, if phi x equal to c, the level surface, or simply a surface in R cube. Then P0 in a point with R0 is the position vector, be a point on S, and P is any point on this tangent plane of S at point P0. So P this the T is the tangent plane at the point P0 on this surface, and P be any point with the position vector R. So P0 P vector, this R vector minus RG vector is a vector on the tangent plane. The equation of the tangent plane at P0 is the R vector minus R0 vector dot gradient of phi at the point P0. This is equal to 0. This is the equation of the tangent plane at P0. Again, if P R be a point on the normal P0 in, then R vector minus R0 vector is collinear to the gradient of P0. So the equation of the normal at P0 to the level surface S through P0, this is the r vector minus r0 vector cross gradient of phi at the point P0 equal to 0 vector. This is the equation of the normal at the point P0 on the level surface S through P0. Here we some workout example, do some workout examples. This function fxy, x square plus y square z square, find the directional derivative of f at the point P1 to 3 in the direction of the vector alpha I cap plus 2j cap minus 2k cap. Also find the unit normal to the surface x square plus y square plus z square equal to 14 at P. So alpha cap is this, alpha vector by mod of alpha vector, grad of f is this, and grad of f at the point P1 to 3 is this. The directional derivative of f at the point P in the direction of alpha is given by this directional derivative along the alpha cap fp equal to grad of at the point P dot alpha cap. So this is the minus 2 by 3 is the answer of this directional derivative in the direction of alpha cap. Now second part, also find the unit normal to the surface x square plus y square plus z square equal to 14 at P. Let phi equal to this, grad phi equal to this at the point P1 to 3, grad phi equal to this, and mod of gradient of phi at the point P is this. The required unit normal to the surface phi equal to 0 at P is given by plus minus grad phi by mod of grad phi, and this is the required answer. Example 2, find the directional derivative of phi is this at the point 1, 2, 1, 3 in the direction parallel to the line whose direction cosines are proportional to 2, 1, 2. Here phi is this, grad phi is this, at the point P, grad phi at the point P is this, and the vector parallel to the line with direction cosines 2, 1, 2 are given by u vector, this 2i cap plus j cap plus 2j cap, 2, 1, 2, and the u cap is this, and the directional derivative of phi at the point P is this, d phi ds at the point P is grad phi at the point P dot u cap. Hence the answer is 11. Next example 3. In the what direction from the point 1, 1, minus 1 is the directional derivative of phi? This is maximum. Also find the value of this maximum directional derivative. Here phi is equal to this, grad phi is this, at the point P, 1, 1, minus 1, grad phi at the point P is this. Now the directional derivative of phi at the point P is maximum in the direction of grad phi P, that is along the 2i cap minus 4j cap minus 8k cap, and its maximum value is mod of grad phi at the point P. So this is the root over 84. This is the answer. Next example, for the function phi is this, find the value of the directional derivative making an angle 30 degree with the positive x-axis at the point 0, 1. Here grad phi is this. So at the point 0, 1, grad phi equal to minus j, and unit vector u cap in the xy plane along the direction making an angle 30 degree with the positive x-axis is u cap is equal to cos 30 degree I cap plus sin 30 degree j cap. So this root 3 by 2 I cap plus 1 half j cap. So the required directional derivative of phi at 0, 1 along u cap is given by this, answer is minus half. Find the angle of intersection of the surfaces this and this at the point 2, minus 1, 2. Let phi 1 is this surface and phi 2 is this another surface. So this is the phi 1 surface and this is the phi 2 surface, and this grad phi 1 is this, grad phi 2 is this. At this point P 2, 1, minus 2, the normals in 1 and in 2 with respective surface phi 1 and phi 2 are given by n1 vector n2 vector equal to grad phi at the point this and grad phi 2 at the point P. So this n1 normal to this surface phi 1 and this n2 is normal to the surface phi 2. So required angle is the angle between these normals. So theta equal to cos inverse n1 vector dot n2 vector by mod of n1 into mod of n2 vector. This is the required answer. Next example, find the greatest steepness of the rise of the surface phi is this at this point P equal to 3, 4 e to the power minus 5. So grad phi is this at the point 3, 4 e to the power minus 5. Grad phi at the point P is this. The greatest steepness will be mod of grad phi at the point P equal to e to the power minus 5. In the direction of grad phi P, that is in the direction of minus 3i cap plus 4j cap. This is the question. This CC-7 2022 group C, question number 15. Find the directional derivative of x square y square z square at the point 1, 1, minus 1 in the direction of the tangent to the curve x equal to d by t, y equal to sine 2t plus 1, z equal to 1 plus cos t at t equal to 0. Here phi is this function, d phi dt equal to this, which is the tangent vector along the curve mod of d phi dt equal to this. So e vector e cap vector equal to d phi dt vector by mod of d phi dt. So ek vector is this, and putting t equal to 0, because if we put t equal to 0 at the point t equal to 0, we get x equal to 1, y equal to y equal to y equal to 1, and z equal to 0. So we get this result is putting t equal to 0. So if f is a function x square into y square into z square, grad of f equal to this, and grad of f at the point 1 1 0, for t equal to 0, we get this 0 vector I cap 0 in 0 vector. This is the 0 vector at this point. So the required directional derivative is given by f ds at the point 1 1 0, that is the grad f at the point 1 1 0 dot e cap. So this is equal to 0. Next question 2009, and the directional derivative f of the surface this xy plus yz plus zx in the direction I cap plus 2j cap plus k cap at the point 1 2 0, where I cap j cap k cap have their usual meanings. The e cap is the unit vector in the direction of this, so e cap is this 1 by root 6 I cap plus 2j cap plus k cap. Grad f equal to this grad f at the point 1 2 0 equal to 2 I cap plus j cap plus 3k cap. So the directional derivative of the function of the surface f at the point 1 to 0 in the direction of this e cap, this grad f at the point 1 to 0 dot e cap. So we get 7 by root 6 the required answer. Next example, fxyz is the surface x cube plus y cube plus z cube, and the directional derivative of the function f at the point 1 minus 1 1 in the direction j cap minus k cap. So grad f at the point 1 minus 1 1, unit vector n cap along j cap minus k cap is this directional derivative of f at the point 1 minus 1 1 along j cap minus k cap is this 0. And the directional derivative of the scalar point function this f xy plus yz plus zx in the direction I cap plus 2j cap plus k cap at the point 1 to 0. Calcutta University Honors 2009. Grad f at the point 1 to 0, this grad f at the point 1 to 0 dot this e cap. So answer is 7 by root 6. Find the maximum value of the directional derivative of the scalar point function phi at this point 1 through 3. Find also the direction in which it occurs. Calcutta University Honors 2001 and 2011. Here, grad phi is this, grad phi at the point 1 through 1 to 3, this, the maximum value of directional derivative of a function at a point is the modulus of the gradient of the function at that point. So maximum value is the gradient of phi at this point, modulus of this, so 2 root 14. The direction along it occurs is the direction of grad phi, that is in the direction of this, grad phi at the point this 1 2 1 3 2, and grad phi is the must be along the direction of outward drawn unit normal to the level surface phi xy z equal to c at this point 1 to 3, and n cap is the grad phi by mode of grad phi is the direction, required direction unit vector. Next question, this f is the function and the directional derivative of f at the point 1 minus 1 2 the direction of j cap plus k cap. This the answer is this 15 by root 2. This example 2, phi function is this directional derivative at the point 1 minus 1 minus 1. Direction makes an equal angle, positive x-axis, y-axis, z-axis. So e cap is this. E cap is the unit normal parallel to the vector whose direction cosines are 1 by root 3, or 1 by root 3 and 1 by root 3. Find the directional derivative of the function fxy is this at this point 1 2 minus 3 in the direction pq, where q is the point 3 1 2. Question 2014. This e cap is this df ds at the point 1 to 3 is this grad f 1 2 minus 3 1 2 minus 3, and this dot e cap is minus 3. So we get the result minus 11 by 15. 15. Question this function directional derivative to the curve x equal to t, y equal to t square, z equal to t cube at this point. This e cap is this, directional derivative this. But the maximum value of the directional derivative phi which occurs, maximum value of this directional derivative grad phi equal to at this point, grad phi mod of grad phi is this maximum value of the directional derivative of phi at 1 minus 1 is root 89. Directional derivative is direction derivative is this. Next example this, example 7, example 8, example 9, example 10, example 13, example 15, 16. This equation of tangent plane normal to the line of surface this at this point 2 minus 1 5, equation of the normal to this line and the tangent plane normal line equation and the constant p and q such that the surface this and this are orthogonal at this point 1 minus 1 2. So grad phi at this point this, grad psi at this point 1 minus 1 2. The surfaces are orthogonal, so grad phi at this point dot grad psi at this point is 0. So p equal to 5 by 2 and q equal to 1. And the vector equation of the tangent line and the normal plane to the curve this and this. This is the equation of the tangent line is this, and this is the equation of the normal plane of this. There are so many examples here, and you get this, you get the PDF class note in the description box. Thank you for watching this video.